And in this last lecture, we will discuss IR divergences. So we calculated the vertex function in QED yesterday, and we saw that it contained a IR divergence. So this was the vertex function we calculated. And so it should be no surprise to you so we calculated it when the photon was off shell. So it should be no surprise to you that if we attach another pair of fermions on this diagram is still divergent. So our loop integral would be unaffected by fermions we attach to the top of this diagram. So that suggests, and we'll show later in the lecture, that the cross-section for electron, positron to muon, anti-muon diverges in the IR at one loop. And so what I'm going to argue is that this cross-section is not by itself observable. And this IR divergence will cancel with another IR divergent cross-section, namely the cross-section for electron, positron to muon, anti-muon with an extra photon. And we'll see that this cross-section also diverges in the IR. At tree level. And the divergences between these two cross-sections will cancel in a way that I'll explain later in the lecture. And so what is going to, so just to give you a preview, what's going to turn out to be finite is the sum. So I can write this as E plus to E minus with a plus gamma in parentheses. So there may or may not be a photon in the final state.
I think in the power scattering, that cross-section is divergent at the tree level as well, right? And the forward scattering magnitude.
This cross-section?
No, at power scattering.
Oh, yes.
So is that also like an example of this IR divergence? I mean, most textbooks say that this has to do with the infinite range of photons.
That's right. It's related. So again, we have a massless massless state in Babos, massless particle, the photon in the Babos scattering, and that can go on shell, and that gives us the divergence. Related, it's not quite the same as what I'll be discussing. Okay, so only this cross-section, which is just the sum of these two cross-sections, is finite at order alpha cubes. So this is finite. And so before we go into the calculations and I explain why this is divergent, how the divergence is canceled, just want to give you some physical intuition for what's going on, why we might expect these divergences. This is an IR divergence, so it's related, and we'll make this more precise later in the lecture, to the fact that if the final photon is extremely soft, that is, has extremely low energy, we can't really tell if it's there in any, with any realistic detector. Any detector has some minimum energy that it can measure, some minimal angular separation. So if it's two particles that are going precisely or very close to the same direction, with some tiny angle separating them, a real detector couldn't tell them apart. And so the only thing we could really observe is we can say that there's an electron and a positron in an initial state, there's an electron and a muon in our final state, and we can say that there's no photons above a certain energy that are separated by more than a certain angle from the other particles. So that's the only statement we could actually make about what's going on in the experiment. And as we've seen many times, only things that we can actually measure in QFT, do we have any reason to expect them to actually be finite. So the same thing is going on here. And so these IR divergences are associated with massless particles. So in QED, we have one massless particle, the photon. In QCD, we have another massless particle, the gluon. So the same sort of thing can happen in QCD and the standard model. So in QCD, we have a massless gluon. But as Francois told you, or alluded to briefly, all QCD is confining. So at low energies, we only observe color neutral states. Gluons are not color neutral. So if there's a soft gluon emitted in some analogous process in QCD, the gluon will turn into a jet. So it will form some narrow stream of particles, so hadrons or mesons, other color neutral particles. So if so there's more to the story in QCD. So if we have a soft gluon emitted in some process, that will emit a jet that ultimately could be observed as a, yeah. And so these jets that come from soft gluon emission are extremely important probes of QCD and the standard model in general. And we'll probably come back to this in the standard model course. OK, so that hopefully should give you some general picture to keep in mind as we go through the calculations. I'll come back and make some of the statements made a little more precise, see how they work throughout the lecture. But let's first look more carefully at this first cross-section, the electron, positron to muon, anti-muon cross-section at one loop, and see precisely how it diverges in the IR. OK, so we will need the tree-level results that you calculated in QFT1. So if you recall from QFT1, you calculated this diagram. And we'll call the momentum of the photon P, which is just P1 plus P2. And the momentum of the muon is P3, and the momentum of the anti-muon is P4. And I'll just quote the result that you all calculated in QFD1. The cross-section as a function of the center of mass energy squared is equal to 4 pi alpha squared over 3s. So this is valid in the limits that s is much greater than the mass squared of the muon, which is much greater than the mass squared of the electron. So this is valid up to order alpha squared. OK, so that's the tree level diagram. At one loop, there are 6 diagrams. So there is this diagram. There is a similar diagram where the vertex correction that we calculated last time is on the electron line. There is a double photon exchange diagram. And there is another one where the photons cross. Finally, there are 2 diagrams where we have a photon self-energy diagram inserted on the intermediate photon. So in the loop here, we can either have an electron or a muon. OK, so that's either 5 or 6 diagrams, depending on how you count. We've got about an hour left, so leaves us maybe 10 minutes per diagram. We'll have to go pretty quick, and that doesn't even let us calculate the other diagram. Fortunately, we can simplify things. If we consider a theory that's almost the standard QED, but with one slight modification, we can simplify things. So we can see how the IR divergences cancel by only calculating one of these diagrams. And so we're going to consider a modification of QED, where we're going to take the charges of the electron and the muon to be different. So nothing in QED requires them to be the same. And so if the IR divergences cancel at some order in the charges, so yeah, they should cancel, the IR divergences should cancel at every order in the charges, even if we make the charges different. So we're going to take the charge of the electron to be QE and the charge of the muon to be Q mu. And this means we'll only actually have to calculate one of these diagrams. And we've actually almost done it. We calculated the hard part. We calculated the vertex function last time. So if we take the charge of the electron to be QE and the charge of the muon to be Q mu, this diagram, this tree level diagram, is order QE times Q mu. It has one vertex where the photon interacts with the electron, one with the photon interacts with the muon. So this diagram will be order QE Q mu cubed. This one will be order QE cubed Q mu. This one will be order QE squared Q mu squared. This one will be the same order. And this one will be order QE Q mu squared times QX squared. So QE, Q mu, QX squared. And so if we want to calculate the, I claimed the IR divergences will cancel between the one-loop corrections here to this electron muon to electron positron to muon anti-muon diagram. It will cancel with the IR divergences in that other process at tree level. That other process is order alpha cubed. So we expect that the cancellation should occur in the cross terms. So if we calculate this cross section to one loop, the tree level result is this diagram squared. The leading correction is the product of this diagram with these diagrams. So if we work to, so if we want to find the order QE squared Q mu to the fourth correction to sigma E plus E minus E plus U minus. This comes from the product of the first and also the last diagram with the tree level diagram. Okay, so this last diagram, if we have a muon running in the loop, will be the same order. However, there's no IR divergence in this one. So I'm going to ignore this diagram for now. And at the end of the lecture, briefly comment on its importance. But it's IR finite, so it's unessential to the argument. Although it should be there for consistency. OK. So we want to calculate, to find this cross-section at this order. We need to calculate this diagram and multiply it by this diagram. So we've done most of the work already.
Yeah. When you say we want to find the cross-section to that order, you mean because the cross-section would involve squaring these diagrams, right? Whereas right?
The cross-section would, we would add up all of these diagrams, including the tree level diagram, and square them. And the square of these diagrams will be subleading to the cross terms that involve the tree level diagram times one of these diagrams. So if QE equals Q mu, all of these diagrams are the same order, and the leading correction would come from the cross term between the tree level diagram with the sum of these one-loop diagrams. OK. So we need to calculate, and we've done most of the work already, what I'll call MV. So this V stands for virtual, the contribution of the extra virtual photon, which is just this diagram. And since we saw yesterday and on Tuesday that this vertex correction is UV divergent, we need to include the counter term. And so let's call the result this. So the electron line is simple. It's just the tree level vertex. So we get a V bar of P2, U of P1, gamma mu P, U of P1. And we get something from the muon line, And let's just give it a new name to whatever shows up in the online. It's gamma mu 2 mu of p. And so we basically calculated gamma 2. So we found yesterday that the vertex that's where this was p going in, this was k, and this was q1, q2, and q1 there was equal to minus IE U bar of Q2 times F1 P squared over M squared gamma mu plus I sigma mu nu over 2M P nu F2 P squared over M squared times U of Q1. And this is what I'm calling gamma 2 mu, except for the counter term. So this gamma 2 mu is this plus the counter term. I'm going to call the counter term delta 1. This is what Tabor called z minus 1. Delta 1 is slightly shorter to write. Okay, so we calculated F1 and F2 yesterday. So we really just need to examine our result. And so we looked at, so I gave you the trivial cross-section in the limit, in the high energy limit, where S is much greater than the electron and muon masses. This will just simplify our calculation. And so throughout, we're going to look at that limit, where S is much greater than M mu squared or ME squared. And so we calculated general expressions for F1 and F2 yesterday. They involved a lot of terms, but they, as we'll see just by looking at the expressions in this limit, they will simplify a lot. So we'll get some simple results if we look at the high energy limit. So first of all, F2, we found yesterday was E squared over 4 pi squared integral dx dy z delta x plus y plus c minus 1 times z 1 minus z m squared over 1 minus c m squared minus x y p squared. And so this was what gave us the anomalous magnetic moment. There we were interested in the limit p was small. Now we're interested in the opposite limit, p is large. So if p is large, then we can neglect this m squared term here. And so this will go as m squared over p squared, which goes to 0 if p squared, which is s, is much greater than m squared. So this term is unimportant. We can forget about this term. Okay, so that just leaves us with this other term. And okay, so and this term we saw yesterday was both UV and IR divergent. Tibra showed you how to regulate the UV divergence using dimensional regularization. I'm going to do it using polyphilars. It'll make it a little bit more clear which divergences are coming from the UV versus the IR. So polyvolars basically corresponds to replacing the propagator with the same propagator, the photon propagator, minus some heavy fictitious particle, sometimes called a ghost particle, that has a large mass lambda. And so if we repeat our calculation, we'll have our original term, our original expression for F1, and we'll have a new term where the denominator is changed. So this k minus q1 gave us some term in the denominator. We now have a new term, lambda. And if you just go through it, our derivation yesterday, you'll see that the only change is that delta, which was our denominator, goes to delta plus z lambda squared in the new term. So we just have two copies of our expression from yesterday. One has this shift. And we also have an IR divergence. So we need some way to regulate our IR divergence to continue with the calculation. And the simplest way to regulate the IR divergence is to just assume that the photon has some small non-zero mass. We'll take to 0 at the end of our calculation. So we'll say that photon has some mass squared m gamma squared. And if photon had a mass m gamma squared, that would also only change our denominator. The photon propagator would have a new term, and so it would change the denominator of both terms. The two terms being our original term and our new polyvolars term. And so after these changes, it's the same calculation we did yesterday, just with some minor changes, which I won't go through. What we find is that F1, which we said before was at tree level 1, so we'll pull out the 1, and we define this little f, which contains the loop correction. I'm going to separate out the counter term from f. With these changes, f takes the following form. So we got the integral over our Feynman parameters. This is all unchanged. The new term gives us a log of lambda squared, z lambda squared over delta plus z m squared. And we have our other term, which is the same. The numerator is the same as before. Our denominator just has a new term that will regulate our photon mass. So this is if we set m gamma to 0 and take m gamma to 0, this term is precisely the same as the term we saw yesterday. And this new term just comes from the Pauli-Villaris regulator. And so we can fix the counter term by demanding that f of big F of 0 is 1. So if we demand f of 0 is 1, that tells us that delta 1 is minus f1 of 0, which means that this term will go away, and we just are left with this term, an integral over the Feynman parameters, which will give us a factor of a half. So we are almost there. All we need to do to calculate the cross-section is evaluate the integral over the Feynman parameters. Which I won't do on the board. I'll just go with the result. So if you want to go through it, you can check the intermediate steps. The first two integrals are straightforward. The second one, or the third one, is a little bit harder, but still doable. And if you evaluate them carefully, you get some real terms, as well as some purely imaginary terms. That comes from carefully remembering the I epsilon. And get another real term. And other terms that vanish when we set the photon mass to 0. Okay, so we're looking for the cross term between this amplitude and our tree level amplitude. So that means we want to calculate is 1/4 sum over the spins of mv, which is the amplitude we just calculated, times the tree level one, which I'll call m naught. I think this is a minus sign. Okay, and so this will just give us 1/4 p to the 4th over p to the 4th. So when we evaluate these cross terms, the electron line is the same in both the tree level and our one-loop diagram. So that's just going to give us the same trace that you would get if you were calculating the tree level amplitude squared for the electron line. We'll get P2 slash gamma mu P1 slash gamma mu. And for the muon line, we'll get one factor of gamma 2 another factor of P4 slash gamma mu, and plus the complex conjugate. So we get basically one gamma from the, so this comes from the tree level diagram, this comes from the one loop diagram. And so we saw that gamma 2 was F1 gamma mu plus I sigma mu nu over 2m p nu F2. The gamma mu nu contains two gammas. So this is a trace of two gammas. So this term doesn't contribute. We already saw it vanished because F2 vanished, but now it really vanishes. For two reasons. So this term's unimportant, so all we need is this F1 term. And note that it's because we're calculating mv dagger m naught plus m naught mv. The terms that will contribute will only be the real part of f. So m naught I m naught has three factors of I. It has, so I m naught was this diagram. So it has three factors of I. So one I from each of the vertices, one from the propagator. So m naught is purely real. So that means that when we calculate this, only the real part here will contribute. And so that tells us that sigma v, which is the what I'll call this correction that we calculated to the cross section, it's twice the real part f p squared over m squared plus delta 1 times sigma naught. So this is because gamma 2 is proportional to gamma mu. It just has some constant factor out in front. And so if we pull that factor out in front, this trace is precisely the same trace that we would do when we're calculating the tree level diagram squared. So that's where this term comes from. And so we're done. We have, and that our result is e squared over 8 pi squared sigma naught minus log squared and gamma squared over p squared minus 3 log and gamma squared over p squared minus 7 halves plus pi squared over 3. And the essential feature of this result is this first term, which is known as a Sudakov double log. So this is characteristic of IR divergences. So it's two divergent terms if we take m gamma to 0. If we only had a log term, we might think that we could fix this problem by demanding that the cross-section at some value of the momenta was finite, and that would make it finite for all values of the momentum. But the fact that we have this double log means that if we try to say that sigma v of, at some scale, center mass energy squared S1 is finite, and we want to use this formula then to determine the correction. at some other scale. The fact that we have a double log means that this difference will be proportional to minus log gamma squared over S1 minus 3 log S2 over S1 plus log squared m gamma squared over S2. So even if we somehow demand that at some particular scale it's finite, it's going to be, we'll still have the higher divergences at every other scale. So we can't fix the problem in that way. So the only way we can resolve this issue is by abandoning the idea that the electron positron to muon anti-muon cross-section is observable. So this is not observable. And we have to include contributions with different final or initial states. And as I mentioned at the beginning of the lecture, this IR divergence will cancel with the IR divergence in the tree level cross-section for electron-positron to muon, anti-muon with an extra photon. And so there are two diagrams here. Two diagrams that are order Q. So this diagram here is order QE Q mu squared. The amplitude is. So the cross-section will be the same order as the corrections we just computed, as is this diagram where the photon is radiated from the other muon, from the muon instead of the anti-muon. There'll be other corrections if we set QE to Q mu. That would be the same order where a photon was radiated from the initial state instead. But if QE is different from Q mu, these are the only diagrams that contribute at this order. Okay. And let's just label our lines. And here we've got P1, P2. And so the difference between these two diagrams is simply the momentum carried by the fermion line. And so the amplitude is, we get from the electron line, following the line backwards, V of P2 bar, gamma mu, U of P1. We can put the photon propagator here. Then we have the contribution from the muon line, which has a bunch of factors. Okay, so it's a lengthy expression, but it actually simplifies a lot. So notice that we basically can think about these diagrams as consisting of two stages. So first we have an electron and a positron that form an off-shell photon, which then decays to a anti-muon, muon, and a real photon. And so we can, the way we'll calculate this is by treating the two processes separately. So this part here, think of as describing the creation of this off-shell photon, which then decays to a muon, antimuon, and photon. So in the, it tells us that, again, we're going to work in this limit. The center mass energy is large. And the sigma r for the real emission cross-section is then just an integral over phase space, sum over the final spins and polarizations, average over the initial spins and polarizations, or spins, over 2s, which we can write as e squared over 2s cubed L mu nu x mu nu. This L is going to describe the E plus E minus to gamma star, and X will describe the gamma star to U plus E minus gamma. Okay. So L mu nu, we're going to, in the L mu nu, we'll put all of the factors associated with the initial electron. I include the sum over the initial spins, or the averaging over the initial spins of V bar of P2, gamma mu, U1, and square. And so this is simple to evaluate. You evaluated the same thing when you computed the electron, positron to mu and anti mu1 cross-section at tree level in QFT1. And one of the intermediate steps you did was that this becomes trace P2's gamma mu P1 slash gamma nu. And so this, we've thrown away the mass term, so we're assuming here again that S is much greater than mu squared, and hence much greater than me squared. And you can evaluate the trace. You have evaluated the trace. I'll just quote the result. So just evaluating traces of products of gammas. Okay, and so that's the electron part. Very simple. Now let's look at the muon part. So to avoid having to write this lengthy expression over and over again, I'm going to call this part here S mu alpha. And let's just look at the structure of x mu nu. X mu nu is the integral over the phase space for the final particles, the sum over the final spins and polarizations. And we've got U bar of P3, S mu alpha, V of P4, V bar of P3, S rho nu, U of P3, epsilon alpha, P gamma, epsilon star beta, P gamma. And using the familiar tricks, we can just write this as integral over the phase space of a trace of P3 slash S mu alpha P4 slash S beta nu G alpha beta. Just if we do the sums over the spins, we get the trace. Okay, so this would be a lot more convenient to evaluate if we were fully contracting the S's. That would simplify our lives a lot because we've got lots of nice identities for evaluating traces of gamma matrices where the indices are contracted. So fortunately, we can simplify things a lot by, again, noting that the Ward identity holds off shell. So that implies that P mu nu, P mu x mu nu is 0. So since x here, since we're integrating over all the final momentum, P3, P4, and P gamma, subject to this constraint that overall momentum conserves, so the center, we said that the center of mass energy still has to, or the total momentum has to add up to P1 plus P2. So x mu nu is actually only a function of p, the total momentum. If it's only a function of p and this ward identity holds, then that tells us that x mu nu has to take the following form. It has to be this term. It's like the momentum space. It shows up in the momentum space kinetic terms for the photon times some scalar function of p squared. And so that tells us that L mu nu, x mu nu, is P1 mu P2 nu plus P2 mu P1 nu P2 mu minus 1/2 p squared g mu nu p mu p nu minus p squared g mu nu x of p squared. So using the fact that p is just the total momentum, so p is p1 plus p2. This is just some straightforward algebra to show that this is just s squared times x of s, which we can also write as minus s over 3 g mu nu x mu nu. So plugging this into our result for sigma r tells us that sigma r is just some prefactor times g mu nu x mu nu. And so we can think, or we can write this as sigma naught is minus 2 pi over s e squared g mu nu x mu nu. So we can think of this g mu nu as minus g mu nu is just coming from the sum over the initial polarizations of our off-shell gamma. So we're thinking of the process as e plus e minus to gamma star. And so since it's an intermediate, or it's actually some intermediate process, we're summing over all possible polarizations there. So so we factorized our cross-section, and we see that the effect of this is that we have now we're contracting x mu nu with g mu nu. So in that trace, we've got all of our gammas fully contracted, which will make evaluating them much simpler. So this is a let's say if I'm not going to go through the algebra, but if you did want to go through the steps, doing it this way, using this word identity will save you at least a page of algebra. So we're almost done. Before I can write the result, just need to remind you of some notation. So in QFT1 homework 2, you evaluated this phase space. This is a 3-body phase space. And what you found is that the phase space was S over 128 pi squared times an integral from 0 to 1 minus beta dx1 integral 1 minus x1 minus beta 1 minus beta over 1 minus x1 dx2, where the x's could be written in two ways. You could write them as 1 minus p4 squared over p squared, which is also equal to 2p4 dot p over p squared, if because we're treating p4, which is the anti-muon, as massless. And similarly for the muon, and the photon, which we have so far not discussed, we need to treat as massive. So if we just set the final photon mass to 0, we'll have an IR divergence. So we can regulate it in the same way we did before by introducing a photon mass. So in that case, this final expression will change. And we get an extra term from the mass, m gamma squared over p squared. And this is what I've defined to be beta. So we have the same photon mass to regulate the IR divergence. Okay, so the only thing left to do is evaluate the trace. I won't do that. Let me just quote the result. So then we can see what it means. Extract the physics from it. It's most easily expressed in terms of these variables that you looked at in your homework. Okay, so the trace which is not so bad to calculate if we use the word identity. It's harder without using that. Gives us this expression. So these terms are independent of beta. So and all the other terms have positive powers of beta. So this term is going to diverge if we set beta to 0. And then we also have plus beta squared. Okay, so these two terms have positive powers of beta. So if we set beta to 0, we should get a divergence. And let's do that and see which physical region of parameter space is giving us this divergence. So if beta equals 0, then the integral over phase space of the trace, not write out all the factors, just write it as proportional to this integral beta goes to 0 also in the phase space integral. So it simplifies the limits. And then we have this x1 squared plus x2 squared over 1 minus x1, 1 minus x2. And so this diverges. Not surprising that it diverges. Got 1 minus x1, and we're integrating x1 up to 1. This numerator is finite there, so we'll get a divergence when x1 is near 1, and this is completely symmetric. We exchange x1 and x2, so we'll also get a divergence when x2 is near 1. And so what does that mean? So let's just look at one of these cases. So if x2 is near 1, then so x2 is related to p4 in this way. So it's the it's about the momentum of the antimuon. And so if x2 is near 1, let's work in the CM frame. Center mass frame. That tells us then that E3 is approximately root S over 2. Yep. So in that case, P is just root S over 2, 0, 0, minus root S over 2. Or 0, 0. Yep. So the CM frame P is root S, sorry, just root S, 0, 0, 0. So if x is 1, then P3 should be root S over 2, and if we choose our coordinates correctly, root S over 2. And so that tells us then by momentum conservation that P4 plus P gamma has to be root S over 2, 0, 0, minus root S over 2. So that means that P4 plus P gamma squared is about 0, or 2 P4 P gamma is about 0. So we're working the limit where all of our masses are approximately 0, so the P4 squared, P gamma squared term go away. But P4 P gamma is E4 E gamma times 1 minus the cosine of the angle between them. So this tells us that if this is 0, then either E4 is 0, or E gamma is 0, or cosine theta is near 1. So those are the possibilities. And if we looked at the region where x1 was near 1, we'd find the same thing, that either E3 or E gamma would have to be 0, or the angle between E3 and E4 was 0. So there are two kinds of possibilities. So the first possibility is E3, E4, or E gamma is 0. This is what's called the soft singularity. So this is probably, so soft meaning low energy. It's probably the first thing you think of when you think of an IR divergence, is where some energy or mass scale is going to 0. We see there's also another possibility. Gives us the same effect. It's where cosine of the angle between 3 and gamma, or cosine of the angle between particle 4 and gamma, is about 1. And this is what's called the collinear singularity. So this is what I meant. Right, at the beginning of the lecture, I said these IR divergences can also come from a finite angular resolution of the detector, not only finite energy resolution. So we can't distinguish, a real detector can't distinguish if we have a sufficiently soft particle in our final state. It also can't distinguish if particles are traveling too close to the same direction. Okay. So this is where the singularities are coming from. You can see that the singularities are coming from either some particles becoming soft or collinear in the loop integral. We'll look at that in tutorial a bit to see that its IR divergences really come from one of these two types of divergences in all cases. That's not as obvious from what we did in the loop calculation, but it's also true. And so the only thing left to do is I claim the divergences will cancel. Have to compute this integral with beta non-zero. And I won't do that on the board, but the result is, I want to check, 8e to the 4th log squared beta plus 3 log beta. These two terms look very familiar to what we found before. Remember, beta is m gamma squared over s over p squared. They come with the opposite signs of what we found before. It's not an accident. And then we have some finite piece. And some other terms that are proportional to beta, or positive powers of beta. And so if we add together, put this result back into our formula for the cross-section, we get that this real emission cross-section is e squared over 8 pi squared times our tree level cross-section log m gamma squared over s plus 3 log m gamma squared over s minus pi squared over 3 plus 5. And these are precisely the same divergent terms we found earlier with opposite signs. They cancel. And so what we're left with is that sigma r plus sigma v is 3e squared over 16 pi squared sigma naught. And so remember, this was just the sigma v was just the correction. So we have to add back in the leading order term to get the total cross-section at this order, which is the tree level cross-section plus 3e squared over 16 pi squared. And so this is our final result. You may wonder about the other diagram that involved the loop, the self-energy diagram on the intermediate photon. So that was IR finite, so it won't affect any of the cancellations of the IR divergences. It is the same order as the diagrams we were calculating if the particle running in the loop is muon. And the effect of that diagram will really just be to change E from the renormalized coupling to the scale-dependent coupling. So we'll just this E will be just the E that Tibor told you about on Tuesday. So that will be just some minor change to this correction if we include that other diagram. And so this process that we've gone through is very general. The IR divergences will cancel as long as we restrict ourselves to asking questions that are measurable. So we saw here that we had to sum over different possible final states. If we went to higher order, there would be more than just the 2 possible final states, even in this process. If we went, computed the order QE to the 4th, Q mu squared, we'd also have to consider corrections to the initial state. Yeah, sometimes we have to compute corrections to the initial state. But in general, if you consider sum over all possible indistinguishable initial and final states, you're guaranteed to get a finite result. So we've seen that the observables are not the same as the observables we thought before. This process is, these IR divergences are really generally present whenever we have a massless particle. So particular massless particles we know of in nature are the photon and the gluon. So in both QED and QCD, these processes are extremely important. Particularly for QCD, where the gluons can form observable jets through strong interaction processes. Any questions?
Usually we have divergences in the UV. We say that they originate from our expansion breaking down or perturbation theory breaking down, right? So how does it relate to IR divergences? How can we think about them in terms of perturbation theory, I mean effects of perturbation theory, or is it a physical thing that is going wrong? Is it what you said last was that we should only ask questions which can actually, we can actually answer by doing the measurement, right? So how is that related to the perturbative structure?
To the perturbative structure. So, so we saw that. So the divergences, which types of divergences we'll get for any particular diagram will change at each order in the perturbation series. So we saw that this log squared beta was present at order alpha cubed. If we went to higher order, we'd get more divergences that would cancel. So if we went to sufficiently high order, we'd also have to consider not only So if we're interested in electron, positron to muon, antimuon scattering at sufficiently high order, we'd also have to consider double real emission diagrams. So the way I presented the
we're at low energies, right?
Uh-huh.
Low energies.
Right.
I wouldn't expect anything to blow up, so it has to come from like a different origin. You know, and the UV, fine. I mean, something can go wrong maybe, but here I would expect that. I mean, perturbative expansions definitely make sense because you know, the interactions are almost negligible at these low energies. So I would expect that this works, but.
The origin, the physical origin, is one of these two reasons. So either we have a very soft particle or a collinear particle. So if we look at our real emission diagrams, so if we set, say, the photon energy to 0, this propagator goes on shell. So that's where the divergence is coming from. This, if this goes to 0, this goes on shell. Similarly, if the photon is collinear with the antimuon, we'll also send one of these propagators on shell. So that's where it's coming from. Any other questions? Yes.
If the mass of the photon acts as a regulator, shouldn't we be taking it to 0 maybe at the end and removing it somehow?
We are. So after we add the real emission to our loop corrections, this is independent of beta, so or independent of m gamma squared. So we can then send m gamma to 0, and our result is already independent of the mass of the photon. So.
And for infinite divergences, is it usually the case that it cancels out when you sum over the diagrams, or do you ever have to think about another term, maybe counter terms or something else?
No, you never need to add counter terms. It's always summing over different diagrams.
It always gets to a different fit.
Okay.
Sounds miraculous.
So in some sense, the IR divergence is a counting problem, right?
That's right.
That it's kind of happened also in our the Casimir effect. That somehow we were not counting the soft photons, and because we kind of never see them, right, until a certain threshold, and they would hold independent of perturbation theory. So that's just coming back to Ian's comment that. It's more like we didn't count something. We cannot, observe something until a certain threshold.
So you all have sufficiently high energy. I'll see you later. Bye.